today what we will do is go through some representative CMOS technology, and you will recognize that all that we have studied so far is very relevant, and it is in fact being implemented in state of the art CMOS technology. So what I thought I will do is walk you through some representative nodes. We will start with 180 nanometer generation CMOS technology, and then progressively look at scaling, look at 130 nanometer, 90, 65, 45, 32, each one being 0.7x of the previous technology. Okay. So, let us then start with this. What I will do here is essentially I will make use of these papers which are published in conference called IEDM, which is an annual conference called International Electron Devices Meeting, which is a premier conference in electron devices, and any new device technology which gets developed gets reported in these conferences for the first time. Okay. So, what I have done is that I have taken a series of papers published in past several years, right. We will go through these papers one by one. Of course, we will not really read the entire paper, but I will highlight a few important things to draw your attention to some of the very important technological implementations. Let us look at this paper here now, which is essentially high performance 180 nanometer generation logic technology. Okay. And just to be consistent, 180 nanometer technology and all subsequent technologies of course will be implemented by various companies, right, various foundries, right. Just I have picked papers published from Intel just without any bias to any company, but just to tell you a representative technology, and also with respect to their technology, Intel's technology, we will see how the technology has progressed, right. So, this is essentially 180 nanometer generation logic technology. If you see here 180 nanometer generation logic technology has been developed with high performance 140 nanometer gate length transistor. You see, I had told you that the so called technology node, but the gate length of the transistor could be less than the technology node, right. So, this technology node is 180 nanometer, however, the gate length of the transistor is actually 140 nanometer. It has 6 layers of aluminum interconnects, right. The interconnect in this technology is still aluminum, however, later on you will see that they have migrated from aluminum to copper, okay, in terms of the interconnect. And the dielectric between interconnects, which is multi-level metal interconnect, if you recall we had discussed this in our CMOS process flow. Between one metal level to the other metal level you have an insulator, and that insulator is silicon oxide, except that it is little bit variant of silicon oxide. It is fluorine doped silicon oxide. The idea of doping it with fluorine is to reduce the dielectric constant of silicon oxide. Okay. That is why they say it is a low epsilon. Epsilon is a dielectric constant, because in the interconnects you want to minimize the parasitic capacitances, parasitic resistances, and hence you need to minimize the capacitances. This is opposite of high K gate dielectric. These are low K gate dielectrics. Okay. So, you minimize the interconnect delay and interconnect capacitances. The transistors are optimized for a reduced 1.3 to 1.5 volt operation. You see, the transistors operate at low voltage, right, at 1.5 volt maximum, not beyond that. Okay. Right, the interconnects feature high aspect ratio metal lines and all that, and using this technology they have demonstrated a 16-bit SRAM with certain memory cell size. Okay. And this is sort of a demonstration of the technology, right. What they are showing here is that not only they have developed the transistors, but they have put together the transistor to make a circuit, and in this case the circuit is static random access memory, which is a representative circuit. Eventually this technology is a logic technology, you see here logic technology, not a memory technology. Logic technology will be used to build microprocessors, which are very high end logic chips, but microprocessors on chip will have cache memory, right. So, these SRAMs will be used for cache memories in the microprocessors. These are not going to be standalone SRAM chips to be sold. Okay. So, they have been able to demonstrate that SRAM circuit can also be implemented using this technology. Okay. So, let us then just go through some key highlights here. Okay. and they give the introduction, why do you need scaling and all that, right. That is very typical, right. Now let us come to the transistor, right. So the transistor is sort of illustrated in this figure, right. You have CMOS technology, right. You have N channel and P channel transistor, right. Figure 1 illustrates the structure of the MOS transistor and isolation used in this technology. The isolation, as we know, is a shallow trench isolation, correct, not a low cost isolation. You have made a trench inside the silicon and that isolates the neighboring transistors. Okay, start with the P minus P plus epitaxial silicon wafers, followed by the formation of shallow trench isolation. N wells are formed with deep phosphorus and shallow arsenic implants. They have not used in this particular case antimony and indium yet, okay, but nonetheless they use phosphorus and arsenic combination for N well, while P wells are formed with boron implants. Okay, that is how they are forming these wells. Okay, and then they also have the electrical gate oxide thickness is 3 nanometer. Gate oxide, what they show here is the electrical thickness. When we talk of CV characterization subsequently from next class, we will see what is the difference between physical thickness and electrical thickness. Electrical thickness is always little more than physical thickness. So if they are saying 3 nanometer is their electrical thickness, their physical thickness could be something like 2 nanometer, okay, less than 3 nanometer for sure. And they have ensured that this dielectric has sufficient reliability, as they will demonstrate, and their gate lengths have been patterned using deep UV lithography. It is an optical lithography essentially. Okay. Shallow source drain extensions, remember all that we talked about in terms of source drain engineering. They have used shallow source drain extension with arsenic for NMOS, boron for PMOS. These are source drain extension for N channel and P channel transistors. Halo implants, boron and arsenic, are used in both cases for improved short channel characteristics. Low N plus P plus junction capacitance values, that is fine. Sidewall spacers are formed using CVD nitride, right. Remember the nitride spacer that we talked about, that is in fact used to isolate deep source drain junction from your shallow extensions, right. They make use of that. They use silicide, titanium silicide. Remember the parasitic region that we talked about, after the gating of the transistor there is a contact and in between there is a silicon, and if you convert it into a silicide you get lower resistivity, and in this technology they are using titanium silicide. Okay. So that the typical on poly and source drain regions with a normal sheet resistance of 3 ohm per square. Okay. That is the kind of sheet resistance that you can get, which is a very low sheet resistance by the way. Okay. Okay, so hence this is how the cross section would look. You see, there is a N channel transistor in a P well, there is a deep source drain, there is a shallow extension, there is a spacer which separates the two, and there is a silicide here, and similarly silicide will be on poly as well as on this junction, and this is a PMOS transistor, right, complementary metal oxide silicon technology, right. So this is how you would define the transistor, and then you will have to characterize a lot of things, right. You will have to make sure that the isolation is sufficient, right. For that you need to characterize the breakdown voltage of these that is between this and this, right. If you apply 2 volt it should not break down, the breakdown voltage should be more like 5-10 volt, right. So for all practical purposes these two are perfectly isolated. Okay. So they are essentially demonstrating all these characteristics. You can go back and go through these papers. These papers are certainly available if you are an IEEE member, or if your institute is subscribing IEEE journals, you will certainly have this listed in the IEEE publication. One other important aspect that we had discussed, all these reliability issues. Remember I said when you do the gate oxide reliability, there is something called TDDB, which is time dependent dielectric breakdown. Even though you are going to operate your transistor at very low electric field, such as maybe in this case 6 megavolt per centimeter, right, what you do is that you apply large electric field and characterize the breakdown times, and based on that you sort of extrapolate it and say that okay, in the real use condition certainly this will be reliable up to 10 years. Okay. They have done a similar thing what we have discussed, right. These are typical reliability characterizations. Okay. And here they show typical N channel and P channel characteristics. This is drain current versus drain voltage, the so called output characteristics, which are well behaved, going up to 1.5 volt for NMOS and minus 1.5 volt for P channel transistor. Of course, your N current is more than the P current because of the electron mobility being higher than the hole mobility. Okay. This is subthreshold characteristics. Your threshold voltage is about 0.5 volt or so, and below that this is a IDS in log scale and VGS in linear scale, right. It is a semi log plot really, and this really is a subthreshold slope as we have already discussed. And again notice that depending on whether you have 0.05 volt here or 1.5 volt here, you will have different characteristics. That is essentially due to the Dibble effect, drain induced barrier lowering. If you have larger drain voltage for the same gate voltage, you get larger current, because your drain electric field will influence the injection at the source side, especially in these nanometric dimension transistors. Okay. So, this is just to show that your polysilicon gate, because of the silicidation, has reasonably low resistivity, right. Sheet resistance is of the order of 3 to 4 ohm per square, which is fairly good. These are typical VT versus length plots. Remember what our discussion, there is a reverse short channel effect. I told you whenever you use a halo, invariably you will have reverse short channel effects, and then usual VT roll off that you will have in this region here, right. This region here VT is coming down. This is VT measured at 1.5 volt on the drain, and this is VT measured at 0.05 volt on the drain, and this difference is essentially your Dibble, right. VT at low voltage on the drain is always higher than VT at high voltage on the drain, right. Your Dibble can be characterized based on that. Okay. So, they have NMOS and PMOS devices which have a subthreshold slope of 90 millivolt per decade. Remember, 60 is the best you can get, but you will never get 60 because you have 1 plus CD over Cox term, which is always more than 1, right. So, because of that it will be more than 60. So, they have been able to achieve 90 millivolt per decade, and their off currents are of the order of 3 nanoampere per micrometer. We always specify off current in terms of ampere per width, unit width. Depending on how many microns your transistor width is, you multiply that, you get the off state current. And your on state currents, saturation drive currents are 0.94 milliampere for NMOS and 0.42 milliampere for PMOS. Okay. So, in other words, your on current to off current ratio is almost 10 power 6. It was, if it were to be 10 power 6, then it would have been 3 milliampere here, but it is not 3 milliampere, it is close to 1 milliampere, correct, okay, which is reasonably good on current to off current ratio. This is NMOS, this is PMOS, same story, reverse short channel effect and typical VT roll off. The VTs are negative, again lower drain voltage, higher drain voltage. Okay. Okay, short channel threshold voltage roll off are shown in these figures, right. Threshold voltages at 1.5 volt drain bias are 0.3 volt for NMOS and minus 0.24 volt for PMOS. Okay. And these results are of course better than any previously published bulk or SOI devices. They are trying to say that they have been able to come up with much better devices. Subsequently, they have also made use of these transistor and built what is called a ring oscillator, and from that they extract inverter gate delay. If you were to build a simple inverter, a NOT gate, what is the gate propagation delay? You have an input transition from low to high, how long does it take for output to go from high to low? That is your propagation delay, and they have been able to get the propagation delay, and typically it is very difficult to measure propagation delays of the order of these propagation delays that they have are of the order of few picoseconds, So, you do not construct just one single inverter, because if you want to construct one single inverter, you will have to measure the time resolution of the order of picoseconds. What you do is that you cascade the inverters. A large number of inverters are in series. Very interestingly, if you have an odd number of inverters in series and connect the output of the last inverter back to the input of the first inverter, create a feedback circuit, that starts working as an oscillator. That is why it is called a ring oscillator. Ring meaning you have created an inverter ring. You need to have an odd number of inverter, otherwise it will go to, if you have even number of inverter, it will go to a steady state, right. Input will also be steady, output will also be steady. But if you have an odd number of inverter, you can do this exercise yourself. Output will try to change the input, and it will keep changing, right. It will become a oscillatory circuit. So, you do this oscillator, you measure the oscillator's time period, and you know how many stages of inverters you have, and you back calculate the delay per inverter, okay. And that is what is done typically, and they do it for unloaded ring oscillator, meaning there is no extra load on the oscillator. The only load is the subsequent inverter stage, okay. Operating at 1.3 and 1.5 at room temperature, they have been able to get very low delays of the ring oscillators. We will come to this in a minute, but this is typically what is plotted: gate delay as a function of gate length. If you have a long transistor, your delays are also more. That is why we are scaling, right. I mean, the reason why we scale is that the circuit starts operating faster, as we have discussed in the very beginning. As you start shrinking this gate length, the gate length is decreasing here, the delay is also decreasing. And the nominal gate length for this technology is of the order of 150 nanometer, and at 150 nanometer your gate delays are of the order of 10 picosecond. Again, if you operate this at lower voltage, your delay is little longer, little more, and if you apply higher voltage for this circuit, not very high, I mean if you apply very high voltage, you will break down, okay, then you can decrease the delay a little further, okay. One good way of benchmarking the transistors is to really plot this so called DC performance metric, okay. What is DC performance metric? This is a XY plot with on current on the x axis and off current on the y axis, okay. And the requirement for a good transistor is that for any given off current, whatever that off current is, that, right, let us say 10 nanometer off current, I want to be furthest right of this curve. If you have two technologies, for example, if I have a new technology which looks like this is much better transistor, because for the same leakage current it is giving you much better on state current, right. On state current is much larger, so your on to off current ratio is huge, so that it will be less leaky, it will not consume large static power, at the same time it will be very fast, right. So, it is essentially a 2D plot of off current versus on current, and you want to really create your transistor to really go along this towards the right. And of course, NMOS tends to be for the same leakage current to the right of PMOS, simply because you have much better electron hole mobility compared to hole mobility, okay. But what they are trying to do here is that the field simple, they say this work, and there are some previous works from references, these are empty symbols. So, what they have plotted here is that these empty symbols are to the left of all these are PMOS transistors from previously published papers, and all these empty symbols here are NMOS transistors from previously published papers, and all they are trying to say is that compared to previously published PMOS devices, these are much better, because for the same off current your curve is to the right, you get much higher on current, okay, and that is what you want to generate. The way you generate this curve, by the way, if you want to generate such a curve, you can't generate this curve with a one gate length transistor. What you do is that using the same technology, you print transistors of different gate lengths from 130 nanometer, 150 nanometer, 200 nanometer, 300 nanometer, so on and so forth. As your gate length is increasing, your leakage current decreases, your on current also decreases. So, all these points here you see correspond to shorter gate length, because these are large on current and large off current. All these points here correspond to a longer gate length p channel transistor, and that is how you generate series of these points by characterizing transistors of different dimensions, and you plot a universal curve which is a off current versus on current curve. Similarly, for n channel transistors, these are okay, the transistors which have very high on current and off current, which are coming from very short channel 130 nanometer kind of transistor, whereas along this these are longer channel transistors, okay, and that is how this is generated. And they do the interconnects, interconnect is essentially aluminum in this case, they have not yet used the copper, okay. But the only thing that they have done different in interconnects is to use fluorinated silicon oxide, as I mentioned earlier here. Okay. You see, fluorine is added to a silicon oxide to reduce dielectric constant and improve interconnect performance. The use of SiOF as an interlevel dielectric reduces the dielectric constant to 3.55 compared to 4.1 for undoped silicon oxide. Right? Remember, silicon oxide, the dielectric constant is around 4.1, right, and whereas that comes down to 3.55. You see, thermal oxide, if oxide is grown at, let us say, high temperature 1000 degrees centigrade, then its dielectric constant is more like 3.9. That is what we used earlier when we were talking of gate dielectric. 3.9 we round it off to 4, but here we say 4.1 because this oxide is not thermally grown, it is a deposited oxide, because you already have a metal line and top of metal line you have to put oxide. So, there is no silicon to grow oxide, you will have to do a chemical vapor deposition of the oxide, and invariably these oxides which are done at low temperature, because you already have a metal, tend to have little higher dielectric constant, and hence the dielectric constant is of the order of 4.1. After fluorine doping, it comes all the way down to 3.55. Okay. Okay. So, they actually build a SRAM cell. This is the cross section, I mean not cross section, the top view of the SRAM cell, wherein you have 6 transistors. This is a 6 transistor SRAM cell. This is their interconnect stack, starting from the transistor at the very bottom. These are the contacts, metal 1, via1, metal 2, via2, metal 3, via4, metal 4, and so on and so forth, going up to 6 levels of metals in this case. Okay. And using all this, they have been able to show a working SRAM, and this is what they are sort of summarizing. 180 nanometer generation logic technology has been developed and demonstrated with high performance, reduced power transistors, aluminum interconnects with low epsilon silicon oxide with fluorine doping dielectrics are used to meet interconnect density and performance requirement. The technology yield and performance capabilities have been demonstrated on a 16 megabit SRAM, which operates at greater than 900 megahertz frequency. So, eventually if you are to build a microprocessor, if the cache has to respond at that frequency, it would respond at that frequency, right. So, they have been able to start from the basic semiconductor processes, using all the process integration, build the transistors, demonstrate a simple circuit like ring oscillator, characterize the gate delay and take it forward to make an SRAM cell and show that the SRAM is working, right. So, this is really a demonstration of a technology, but still this technology is still not, after this it may take another year for you to make a real product, okay, because your real product is going to be microprocessor subsequently, right. Then you will have to make a microprocessor, make sure that the yield is good, right, and that requires a lot of optimization. Okay. Okay. So, let us now look at the subsequent technology, which is you know, the 130 nanometer okay, generation logic, again logic technology, right, because Intel does not make standalone memories, right. The only product they offer, and that is their essentially lifeline, is microprocessors, very high end microprocessors, right, and hence this is the logic technology, not a memory technology again. Now 70 nanometer transistors, although it is a 130 nanometer technology, you see the gate length is 70 nanometer. They have dual VT transistors. Remember something that we discussed? There is a leakage power problem, you need to really make sure that you minimize the leakage power, at the same time you need high performance. So, what do? It turns out there are only a few critical parts in any complicated chip. It is important to make the transistors in the critical path very fast transistors, and hence make only those transistors a low VT transistors, and others could be high VT transistors, right. So, as a result of that you get very fast chip as well as low power consuming chip. So, in other words, here you have two flavors of n channel transistors and two flavors of p channel transistors. One is called a low VT transistor and the other one is called a high VT transistor, and hence it is a dual VT transistor technology. And what else? 6 layers copper interconnects, a big departure now from aluminum to copper, because this is the only way to scale the interconnects. Very briefly maybe we will look at the issues in interconnect scaling, but let us get started you know what they have here. A leading edge 130 nanometer generation logic technology with 6 layers of dual Damascene copper interconnects. Dual Damascene is a particular process sequence which is used to realize copper interconnects, right. We will not really go over the details of that process sequence. Dual VT transistors are employed with 1.5 nanometer thick gate oxide. The gate oxide thickness has gone down compared to what it was in the previous generation, operating at 1.3 volt. Previously it was 1.5 maximum, now it is 1.3. You see, high VT transistors have drive currents of 1 milliampere and 0.5 milliampere per micron for NMOS and PMOS, while low VT transistors have 1.17 for NMOS and 0.6 for PMOS respectively. So, two flavors of transistors. Again they have been able to make an SRAM cell, demonstrated SRAM cell, demonstrated the technology on a 18-bit SRAM. Okay. The you know typical process flow is the same thing, except that you have a dual VT, meaning you will have to create two different N wells, two different P wells. So, that doping concentration is little different in two N wells and little different in two P wells, and that is how you get dual VT technology for N and P, which means more photolithography step, little more complex technology, but that is worth it. Only if you do that you would be able to get the best of it. Okay. Okay, so various technological features. This is how a transistor looks, n channel transmission electron micrograph of showing 70 nanometer gate length, source, drain, ultra thin gate electrode, you know, polysilicon, silicided at the top, and so on and so forth. Okay. All else will remain identical. You will use halo, you will use shallow extension, you know, except that you may change the dose because the transistor gate length is going down, especially halo dose you may want to manipulate. Okay. Shallow source drain extension regions are formed with arsenic for NMOS, boron for PMOS, boron and arsenic halos are used. This will remain same. Okay. Silicon nitride is used for the spacer, correct, followed by HVAC. The silicide here is cobalt silicide as opposed to titanium silicide. Cobalt silicide gives you much better lower resistance compared to titanium silicide. Okay. Okay. Again they demonstrate a well behaved NMOS and PMOS, right. The story looks similar, right. You know, you will see similar graphs here, except that now you have a high VT and low VT, two flavors. Okay. And subthreshold plot, drain current in a log scale versus gate voltage, okay, for low drain voltage and high drain voltage. And The Dibble for the 70 nanometer NMOS device is measured to be 100 millivolt per volt. That is how we specify the Dibble, right. What is the difference in Vt per unit voltage on the drain, unit voltage change on the drain, and that is how they are characterizing the Dibble. And this is again the typical off current versus on current, right, and they are sort of saying that okay, you know, this again two flavors, unfilled and filled, high Vt and low Vt. There are two flavors of PMOS and two flavors of N channel transistors. Okay. These are some important metrics such as VDD, gate length, oxide thickness. You know, they are comparing 180 nanometer generation, which is a previous paper that we discussed, and this generation. Supply voltage from 1.5 to 1.3, gate length from 130 to 70, oxide thickness from 2 nanometer to 1.5 nanometer, and so on and so forth. Okay. You see off current has increased a little bit from 3 to 10 nanoampere per micron. Okay. Typical threshold voltage roll off, threshold voltage versus gate length, N channel, P channel, N channel positive and P channel negative Vt, low drain voltage, high drain voltage. This is because of Dibble. Okay. This is now high Vt and this is the low Vt transistor. So, again they characterize delay, the ring oscillator. Now, they have depicted in slightly different fashion. In the previous paper you saw delay plotted against gate length. Here delay is plotted against off state current of a transistor. Remember, off state current is inversely related to gate length. In other words, if you had to plot gate length here, this would have been a lower gate length, maybe 100 nanometer here, maybe 200 nanometer here, maybe 500 nanometer here. Okay. 500 nanometer will also have, I am sorry I got it the other way around. Okay. This would be 100 nanometer. Okay. This would be, let me see if I can delete this. Okay. Yeah, let me just take it away. Okay, that is okay. So, this needs to be sort of reversed. Okay. Okay. Right, 100 nanometer is out here. Okay. 100 nanometer also results in large leakage current. Okay. Longer channel length also results in small leakage current, correct. I mean, let me write it here so that becomes very clear. So, this is 100 nanometer transistor, let us say 100 or 170 nanometer in this case, right. They have gone down to 70 nanometer, right. So, this would be something like 70 nanometer out here, okay, and this may be 100 nanometer and this may be 200 nanometer. So, the gate length is the lowest here and the lowest gate length gives the lowest delay, and when the gate length is increasing, the leakage current also decreases, as is evident here, lower leakage current. Because you have larger gate length, the current on current will also be lower, just as off current is decreasing, on current is also decreasing, and hence you will get larger delays, correct. It is essentially, you know, looking at this delay versus gate length or delay versus leakage current, you know, one and the same essentially. So, chip performance is increasingly limited by the RC delay of the interconnect. Now, why is that? Let us look at what is happening with scaling, right. What have we done over scaling? You know, we have started from let us say technology of the order of 250 nanometer, quarter micron technology, 180 nanometer, 130, right, 90, 65, okay, 45 and so on and so forth, right. And let us look at what happens to delay. We know that as I scale transistor becomes very efficient. In other words, if we are talking of gate delay or inverter delay, over the technology generation, inverter delay or gate delay has been decreasing, and that is why in the first place we want to scale. You build any gate, it could be a NOT gate, AND gate or what have you, right. So called gate delay decreases. Gate delay decreases because remember gate delay depends on transistors, and transistors with scaling become efficient. Smaller transistors are always better, and the so called CV over I metric becomes better as I start scaling down the transistor. What is the story with interconnects? Interconnects, it turns out the story is completely opposite, unfortunately. What is an interconnect? You know, interconnect is a metal line, okay. Let us say this is metal 2 and there may be another neighboring metal 2 line here. This is another line running at the same level, and let us say there is another metal 1 underneath M1. Between these two you have inter-level dielectric, two metal levels, between that you have a dielectric, that is how you have insulated, correct. This is metal 1. What is scaling of interconnects? Scaling of interconnects is scaling the dimensions of the interconnect, just as scaling of the transistor dimension has to come down and transistor distance has to come down, and same here with the interconnects, right. The interconnect, the dimension has to come down. What is the dimension? You see, this is the so called line width, we call it line width. We print the metal line is a long metal line. How long it is depends on where is this metal going from in a chip, from one location to the other location in a chip. This is the thickness, let us say T, and this is length, okay. Let us normalize the length. Unfortunately, the chips are not becoming small, the chips are really becoming bigger and bigger. You would have thought that with scaling, because you are trying to bring down the number of transistors, the chip should become smaller, right. That is why we said 0.7x, so that the chip area comes down, transistor area comes down and all that. But what has happened over the years is that with scaling we also put in more transistors in a new technology. We are not just happy with the performance gain that comes just because of the mere scaling. We want to increase the number of transistors very significantly compared to what it was earlier, okay. So if previously you had million transistors, you want to put 4 million transistors in a new chip, in a new technology, and hence you continue to use the same area or even bigger area, okay. So in other words, if you are looking at a chip, the chip size from one technology to the other technology really does not scale. If anything, it is becoming bigger, the chips are becoming bigger. What is interconnect? Interconnect is essentially a metal line which takes the signal from one location to the other location in a chip, you see. So the message here is that the lengthwise it is not really helping us, it is really becoming as big. So let us look at normalized length, what happens with interconnect scaling. What happens to, what is interconnect delay? Interconnect delay depends on R and C of the interconnect. This is a RC delay due to interconnects. Scaling, I need to scale the width, I need to scale T. If I go from this technology to a new technology of metal interconnect, in that the thickness has come down, the width has come down. What is the implication? Resistance goes up, because your cross section area for conduction is going down. So per unit length, you see, if you have to look at, ask the question, what is resistance per unit length, right, what is L, rho L by A. Let us say I am interested in R per L, it is rho by A. How is A scaling, right? A has T and W, okay. As a result, your interconnect resistance per unit length goes up as K square which is not a good thing, okay. This is not the end of the story. So the message is that interconnect lines are becoming more resistive with scaling, not the end of the story. There is even more serious problem, and what is that serious problem? You would have thought that at least because I am making the interconnect smaller, the capacitance should go down, okay, because capacitance should be due to, let us say, this metal line and another metal line, there is a coupling capacitance and the area for that coupling is T, I mean this that is determined by this width that is coming down, and hence it should go down. Yes, the so called parallel plate capacitance or intermetal capacitance indeed goes down, but there is a more serious issue, and what is that? I am also decreasing the distance between the two metal lines in the new generation of the technology. So, the new generation of the technology has M2 lines which were far apart have been brought very close to each other. So, there is a new capacitive component which is intra-layer capacitance. Earlier this distance was very large, you could have ignored that capacitance. Now, this is increasing very dramatically. So, net result is that with scaling your R is increasing, your C is also increasing as far as interconnects are concerned. C is increasing very dramatically because these interconnects lines are coming close to each other, okay, and hence the RC delay of the interconnects is increasing. So, if you were to look at interconnects in older generation technology 250 nanometer and beyond, interconnects were afterthought, you never bothered about interconnects. They are ideal metal lines, take signal from one location to the other location, they do not contribute any further delay. So, it was non-existent compared to gate delay, your interconnect delay was very low. But what has happened in the recent past is something like this. Your gate delays are increasing, your interconnect delays are increasing, and hence interconnects are becoming bottlenecks, right. It is like, just imagine your road network in the city, you have the fastest driving car, okay, and that is transistor for you, that is a gate for you, but you have a very bad road network, then you are limited not by the speed of the car, but you are limited how fast the roads will allow you to travel, right, and these are the roads, interconnects are the road that allows you to take signals from one location to other location, and that has become a serious problem. And hence you see that in this technology there are a lot of things that are being done to minimize R and to minimize C. In previous paper we saw fluorine was doped to minimize capacitance, and today I mean in this technology we see aluminum is replaced with copper because copper has lower resistance compared to aluminum. RC delay becomes much better, and that is exactly what is done here, okay. And they have optimized this fluorinated oxide, and that gives a K of about 3.6, and this is again the hierarchy of interconnects, and they have used this to build okay. What they are showing here is that if they had used aluminum, you see, with decreasing pitch is two metals are coming closer to each other, your delays are increasing. If you had used aluminum, it would have gone up like this. Because you use copper, you could decrease it, okay. At the same pitch, copper technology gives much lower delay compared to aluminum technology, and that is what they have done, and they have been able to make an SRAM and demonstrate that 18-bit SRAM is operating now at what 1.6 megahertz, much higher frequency, okay. Okay, right. So, okay, actually it is not very clear here, I take back what I said. I mean the previous one was a lower density SRAM, was at 900 megahertz, but this is a higher density SRAM, that is operating at little lower frequency. As you start increasing the density, there is also an impact on the speed of the SRAM that you can build. Whereas the ring oscillators obviously are much more efficient compared to the basic technology is much better. Previous generation was 10 picosecond, 10 to 13 picosecond, now it is a 7 picosecond, right. So, you can clearly see a better technology. And if you go down to 90 nanometer, now what has happened now? 7 layers, 6 layers have become 7 layers of copper. 90 nanometer has a 50 nanometer gate length transistors, okay. From 70 it came down to 50 nanometer now. It is using a strained silicon channel. We have not discussed about strained silicon channel. but very soon down the line you will start discussing strained silicon also. So, we will postpone that discussion for the time being. This uses 1.2 nanometer oxide, it is even thinner than previous generation, and nickel silicide instead of cobalt silicide, it is nickel silicide. Now, there is a some more optimization, and so this is the cross section of a transistor. Channel is strained silicon, 1.2 nanometer gate oxide, 15 nanometer gate length, nickel silicide is shown here at the source drain and at the polysilicon. And they have been able to make a 60 SRAM cell using the technology, right. This here just shows that you have silicon and 1.2 nanometer oxide and polysilicon gate, okay. And typical off current versus on current for N and P channel transistors, okay. And they are just showing here as a function of year different technology nodes. We already looked at 180 nanometer technology, 130 nanometer. In 180 nanometer you had 100 nanometer, 130 nanometer, 70 nanometer gate length, 90 nanometer, 50 nanometer gate length. This is what I said. Now, we have a departure in terms of what gate length you print is actually smaller than the so called technology definition 90 nanometer, but in the past they were exactly identical, okay. We have had a discussion on this in the one of the earlier lectures. Why nickel silicide? Because with scaling cobalt silicide will start increasing the resistance, whereas nickel silicide gives very low resistance, and that is why they have gone to nickel silicide, okay. Again multi-level metal interconnects. Now, instead of fluorine doped oxide they have done carbon doped oxide, again a new improvement, that is how you need newer and newer materials. K has come down to 2.9 instead of 3.5, again to decrease the RC delay of your metal interconnects, okay. And they again show that with carbon doped oxide you can get significantly lower RC delay as you start decreasing the pitch, as compared to aluminum oxide with fluorine doped oxide, aluminum with fluorine doped oxide, copper with fluorine doped oxide, and this is copper with carbon doped oxide, okay, which is much better. And they have been able to do an SRAM here, and this SRAM operates at 2 gigahertz, okay, which is much higher frequency, okay. I suspect that the previous paper that probably should have been 1.6 gigahertz, that could be a typo there, rather than 1.6 megahertz. That is more like it, because on 180 nanometer you had a 900 megahertz, very close to gigahertz, right, and then you have 1.6 gigahertz, and now you have about 2 gigahertz or little more than 2 gigahertz, okay. So, this is about 90 nanometer, and if you come to 65 nanometer, all that has happened really is gate length has scaled down further, 35 nanometer, 8 levels of copper interconnects, interconnect hierarchy is also becoming more complex, and SRAM cell is also shrinking. Continue to use nickel silicide, okay, and let us see if there is anything that I want to highlight here. Okay, so this is a typical trend, right. So, on a 65 nanometer technology the gate lengths are 35 nanometer. This is a typical cross section of a transistor, okay, N and P channel transistor. ID VDS characteristics and subthreshold characteristics. This is off current versus on current, typical DC performance metric, okay, and this is the same for PMOS transistor. This is a very nice cross section showing different levels of metal interconnects, okay, and okay, they have made an SRAM, this is a 70 megabit SRAM test vehicle, and they have been able to show that this SRAM operates at frequencies close to 2 gigahertz, right, and that they have been able to demonstrate, right. No major departures. Then at 45 nanometer you see very significant departure, and what is that? For the first time you see high K gate dielectrics along with metal gate, okay, here high K metal gate for the first time. 45 nanometer logic technology and transistors feature 1 nanometer EOT, that is equivalent oxide thickness, but they actually use a hafnium oxide gate dielectric which is thicker than 1 nanometer. They use a high K gate dielectric, dual band edge work function metal gates, 2 different metals, one for N channel, one for P channel transistors. Okay. So, what they have been able to show here is the following. Okay. You see this is gate leakage here, okay, and this is oxide thickness EOT. When you use SiO2, EOT and SiO2 are one and the same. Okay. You see from previous this is a 45 nanometer generation. At 65 nanometer generation they were not able to scale the gate oxide thickness, because the leakage current, as we started decreasing the gate oxide thickness, leakage current suddenly started increasing because of direct tunneling current. And because from 90 nanometer to 65 nanometer they did not have a mature high K gate dielectric technology, they could not scale the oxide thickness. They kept the oxide thickness as is, and then the leakage current kept at the same time, same level. Now with the high K technology the EOT came down, but the leakage did not increase, the leakage also came down, right, because it is a EOT of 1 nanometer, but indeed it is a thicker physical oxide, direct tunneling is suppressed, and hence you got the best of the world, right, you got lower EOT and lower leakage current. That is why you want to use high K gate dielectric. That is illustrated very nicely here, showing the trends in different technologies. Okay. So, this is a high K, and metal gate is different for NMOS and PMOS. Okay. Okay. So, what is the typical process flow? They do a STI, shallow trench isolation, wells, and adjust the VTs. They deposit high K gate dielectric using atomic layer deposition. ALD is atomic layer deposition of that dielectric. They do a disposable gate, metal gate, remember the discussion that we had. So, polysilicon is done as usual, gate patterning, source drain extension, spacers, everything is done, source drain formation, nickel silicidation, and then you deposit an insulator. Then poly opening, you etch back the poly, okay, poly is removed. That is what we mean by disposable metal gate. Poly was sitting there as a placeholder, so that you get self aligned transistors. Then you do one metal for PMOS transistor, which has a work function appropriate with P channel transistor, do patterning of the gate, and then again do a NMOS work function metal deposition. You need 2 metals for defining 2 different kinds of transistor, and you complete the transistors, and then of course you do the multi-level metal interconnects. So, this is again to show that with high K your gate leakage has come down very dramatically. If you had used the silicon oxide or even so called nitrided silicon oxide, you would have had a very high leakage current, but now that is not the case. This is the typical VT versus gate length threshold voltage roll off that we have seen, measured at low drain voltage and high drain voltage. That is for N channel, and this is for P channel transistors. Okay. Typical off current versus on current plots, right, this looks similar, everything looks similar. And now typical delay versus off current, remember this is how it looks. When you have very large off current, it means the smallest length transistor has the highest leakage current, and hence because you have built the inverter using the smallest length transistor, you have the best delay that you can get, and the delays are now of the order of very low delays of 5 picoseconds or even less than 5 picoseconds. Okay. Reliability of the transistors, again they have characterized TDDB, by accelerated testing, extrapolation, right, just to show that these high K gate dielectrics are as reliable as silicon oxide. Okay. Then they have actually made not only SRAM in this case, they have actually made a microprocessor. They have made a single core microprocessor and dual core microprocessors, okay, and been able to show that you can actually get a fairly good circuit working with all these new technologies, high K, metal gate, and so on and so forth, right. And that is what happened in 45 nanometer technology. And in 32 nanometer technology, the high K and metal gate continued, right. It continues to be high K and metal gate transistors, right. We have stuck to that right now. Going forward, we will continue to use high K and metal gate, but it is called second generation of high K, and they have tried to do some optimization, improve the hafnium oxide performance, improve the metal gate performance, and so on and so forth, right. So, 32 nanometer, the actual gate length is much lower than a little lower than, not much lower than, little lower than 32 nanometer. This is just showing that previous generation technology, this is a 32 nanometer technology, and off current versus on current, the typical plots that we have seen, all these are off current versus on current plots, right, trying to indicate that they have been able to optimize this transistor for a given off current. They have been able to get as large on current as possible, okay. Typical output characteristics, IDS versus VDS. Notice that the difference between N and P has come down. If you recall 180 nanometer technology, your P channel current was almost 50% of the N channel current. Now, using the so called strain engineering, which as I said will be discussed in one of the future classes, we are able to enhance both electron and hole mobilities, and so much so that the hole mobility can approach very close to electron mobility, and that is why you do not see a huge difference between electron and hole mobility and electron and hole current, N channel and P channel current, okay. The difference has come down. This is a typical subthreshold plot that you would see, and typical VT versus length plot. VT is decreasing with decreasing channel length, right. So, all this is consistent with what we have been discussing, and they have again made an SRAM, and they demonstrate that SRAM works fairly well with this 32 nanometer technology, right. So, what we have been able to do in this lecture is really to look at representative CMOS logic technologies, not memory technology. These technologies are not for DRAM fabrication, not for flash memory fabrication, not for even SRAM fabrication, but to make a very high performance microprocessors, okay. So, their performance is the key. You want to make the transistor which gives the lowest delay, and various techniques we have seen, right. All the source drain engineering, channel engineering is consistently used in all these transistors, and as we have continued to scale the technologies, we have transitioned from silicon oxide to high K gate dielectrics to metal gates, and so on and so forth. Similarly, in the interconnect arena, we have gone from aluminum and conventional silicon oxide to doped silicon oxide, copper, and thereby minimize the RC delay of the interconnects very significantly, right. So, hopefully now you should be able to read up any CMOS technology paper and be able to understand that based on all the discussion that we have had so far, right. So, we will stop this lecture today, and starting from next lecture we will actually start looking at electrical characterization, that is CV characterization and IV characterization, okay.